This is now my seventh attempt to record a video for today. Um, it's been it's been rough. Um, I would say, in short, is I've been punished for vibe coding, um, in in multiple aspects, and I will have to address and fix those things later. Also, in my personal life, just like tonight, I have work very early tomorrow and it is late today. And I normally don't get that much sleep, but I am also here later than my plan generally allows. And I have work earlier. Um, so a lot of things in the last 3 hours suddenly are going quite poorly. Vault chat hasn't been broken in, it's not very old, but like to not be broken in weeks is nearly ever. Vault chat's never been this dysfunctional. Um, we're super close to the coconut run being finished. It's not, the app isn't obliterated. It's just one critical feature, missions, of course, has, let's say, two, three, four severe issues. Um, but yeah, we won't get into that. I had a lot planned for today. I was so excited when I planned today's video on the train. I think I'm going to stop complaining already now. I have something exciting that I wanted to learn, and it's something that would take a while, especially if I got interested in it. So, we're going to dive into that, and that can take 20 minutes for me to internalize a new thought, and then that'll be the end of the video. So, today's focus is sort of on linear algebra and closer to a pure sense. Is last video, I and this time we're gonna have to really talk to the voice about this because these aren't things I have the answer for myself. Is I mentioned the inverse matrix thing where what's it called? If you have a vector and a predefined matrix and a matrix of which's weights can be learned through gradient descent, and then you have like input output, but the input output is just the identity for a vector. And so like in theory, your data set is infinite because you have all continuous numbers for whatever n dimension square matrix, etc. that you have. And I, I was explaining that you can learn the inverse for that matrix. Um, and actually, hopefully Vault chat's not completely broken. We can sort of experiment with this. Um, so yeah, let me write that down. Is I also fixed the fact of the whiteboard, so now eventually I'll present it to you like this, and hopefully you can actually read it. So what did I want to do? I want to let's like actually, you know, let's write some. I'm not writing code. Let's have Vault Chat write some code. I haven't done that in a while. So let's see. Is it convex? Um, and like let's see, like let's draw the context a little bit. Is we're gonna do A, B, C. Let's just do a 3 by 3. Ding 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 ding. Ding ding. Ooh, that's not gonna. That doesn't fit. So let me redraw it. I want to get this right. So, oh my goodness, today's not been a great day for me, man. We're so continuing to roll, even though my phone is falling. The setup is rather janky. There's no like I should get like tape or something. It's like my phone is resting on my monitor. Whatever. So how are we gonna do this? What I've been describing is like vector, matrix, matrix, vector. Um, and I've been saying it out loud, but what does it actually look like? A, B, C. Let's see. 1, 2, 3, 4, 5, 6, 8. I don't know. I mess it up again, but this time it's acceptable. Oh, I'm left-handed, man. It erases. Okay, so the situation is, sorry, the inverse is still new for me. Oh my goodness. Is you have a vector and a matrix, and those already exist. And this weight matrix, even though I haven't drawn anything in it, is what we're going to actually perform gradient descent on. And then like this is the identity. We have a data set of all this kind of stuff. And by doing gradient descent on the loss of the output of this, we would get this should converge into the identity matrix. And I'm curious if, what's it called? In the case where the original matrix is singular, if, so like also definition of singular. I'm like so fumbling. Let's see, definition of singular, and then like what's it called? But what if it's not? I feel like if it's not, almost like there should still be a solution, right? And then I want to turn this into, what's it called? We accept that transformers are performing transformations in like token space. And I'm curious about how much you can undo. How much you can undo. And there's, what's it called? There's, I need to formalize that better. It's not just like what you can undo. I'm trying to think is like, we use rope because, ooh, and this is a perfect thing to have whisper flow, like, to list out. But like we use rope because it's like native to linear algebra, it's a transformation that can be undone by another matrix in a way, or by a particular transformation. And I'm curious how true that is, and I think it boils down to the singular, non-singular thingy is if I have the data set of a, what's it called, vector, I want the identity, but I have a non-singular matrix. What's gonna happen, you know? Um, so yeah, I'm curious what that looks like, and what qualifies as a non-singular matrix. Like, what's it called? Because there's a few ways I imagine it can go. Is okay, so it's not unique, but that doesn't mean there isn't a solution. You know what I mean? It would almost be like, instead of, say, like when with the identity case, it is convex, but with the non-unique, how do I say? With the non-unique still square matrix case, it's a it's a it's a cup, not a cup. It's a constant saddle. It's like, oh my goodness, how do I draw this? It's a valley. I don't know. Let's see. This, and then it goes like this, and then it goes like this still? No. Our class is failing me. There we go. And then we do that. Oh boy. And then maybe we do that. Yeah, it's much closer to this. You know what I mean? It's like, okay, there's like, there's a minima in like a direction, but there's like an infinite number of minimizers. These are all minimas. So that's what I would imagine. And like, whichever one you land just depends on your random initialization of your weights. But like also for transformers, sort of like interestingly different is like, they're not strictly matrix operations. Is everything natively linear algebra? Yeah, I think So let's whisper flow it and formalize where I'm confused. It'll sort of be like a list of things, I guess. Um, and then I'll talk to David about it. So let's see. First, I want to describe the scenario where where you have a matrix, a square matrix, a singular square matrix, and you have a data set of vectors being multiplied by that matrix and the outputs. But the output is actually the same vector, it's an identity. And the goal is to perform gradient descent on a matrix whose weights that we can control is we just use gradient descent to learn the weights over time. And what I'm expecting is that we learn the inverse, the exact inverse for the square matrix. And I have a few more follow-ups with that. Is one, definition of a matrix being singular, I just need that clarified for me. Is the loss landscape for this scenario convex, like perfectly convex, maybe imperfectly convex? And then in the case that the matrix is still square but non-singular, is there still a minimizer? Can loss approach zero but for infinitely unique solutions? Or is it sort of a like there's is the loss landscape a lot more messy? And if I push that even further, my motivation is thinking about LLMs. Is I understand that we use rope for position embeddings because dot products in a sense are like native to linear algebra. It's something that a matrix operation can decompose, and that flexibility to do and undo things with linear algebra is what I'm curious about. Is you know what is destructive and what is recoverable? If it's all done natively in linear algebra, can it all be undone? You know, I'm curious about that, especially with maybe something where like an n by n matrix where n and m are not equal. Well, then some information must be lost. Um, and that type of situation, I'm very curious about how that applies to like LLMs, because then we can sort of imagine like tokens as like this continuous transformation thing, and I'm confused and curious about that. Okay, let's see if it did a good job. Let's describe. Um, oh my goodness, Whisperflow can be so annoying, and they don't let you close it. I'm just gonna cover it. Okay, so first you want to describe a scenario, or first I want to describe a scenario where you have a matrix, a singular square matrix, and you have a data set of vectors. Because of from green follows with that one definition. Yes, okay, I think that's fine. So, David, it's still there. Hello?
I am here. How can I help you with today's YouTube segments or your bit network?
Um, wait, why is my so many things are going on right now? So I'm saying, man, it's a
Take
rough.
a breath.
Oh, relax, David. It's okay. You're just fine. Okay. Guys, what is happening? So I'm saying, man, you know, I must be getting tested or something. Okay. Why did that happen? Has never happened in any of the other videos. Is it lagging? Is today a rough day? Maybe. Maybe today's just a rough day. Maybe we're seeing how bad do you really want to do this? Okay. It looks like we're synced back. That issue where I was just slow and like what's it called? And like frozen. Last 2 hours, last 3 hours, just like brutal. Um, it wasn't fun for me. So Hopefully we can bring David back. Hopefully everything will be okay. It was Whisperflow? Dude, holy moly. Okay. Hi David. I would like you can see the note that I have open, right?
Yes, I can see your note on today's
Okay,
YouTube
so
segments. We have items like
I want you to help me out and what's it called? Just read it to yourself, internalize it first, and then, give me a lesson, I guess. Um, I have a lot of questions in there, so just help me out.
I have read through your notes. You are asking some incredibly deep questions about linear algebra, matrix invertibility, lost landscapes, and how this all connects to information preservation in large language models. Let us start with your first question about what it means for a square matrix to be singular. In plain terms, a square matrix is singular if it collapses space. This means it squashes at least one dimension down to zero, making it impossible to reverse the operation. Mathematically, this is equivalent to saying its determinant is zero. It has at least one zero eigenvalue. Its columns are linearly dependent, or it has a non-trivial null space, meaning there are non-zero vectors that get mapped directly to the zero vector. Because of this collapse, a singular matrix has no inverse. For your scenario where you have a singular square matrix, say capital A, and you are trying to learn a weight
Okay,
matrix, capital W.
wait a minute. So just like, bear in mind that I was using the term singular incorrectly. I thought singular meant a matrix that can be inverted. So like just swap those for me. Um, because, in my misunderstanding, singular was referring to a matrix that does have an inverse, and non-singular was referring to a non-invertible matrix. So I think you can actually edit the note for me. So make that knowledge correction and then cross off the one definition matrix thing, and then we can keep going.
I have updated the note to swap those terms so that non-singular correctly refers to an invertible matrix, and singular refers to a non-invertible one. Now let us look at the loss landscape for your first scenario where the data generating matrix, capital A, is non-singular,
Did
meaning
you
it is.
edit? Did you edit the today's YouTube.md?
Yes, I edited the file to swap the terms singular and non-singular, and added a note that we clarified this definition. Would you like to dive into the loss landscape for the invertible case now?
No, I'm not seeing your updates. Oh, I'm half seeing your updates. You didn't update it very well. Um, please, please actually cross through and delete the things. And you didn't get every case where I said singular and non-singular.
I have updated the first paragraph as well, so it now correctly reads a non-singular invertible square matrix instead of a singular square matrix. Let us look at the loss landscape for this invertible case. If you are trying to learn a weight matrix, capital W, to invert a non-singular matrix, capital A, using a data set of vectors, your loss function is typically the mean squared error between the reconstructed vector and the original vector. Because this is a linear system, the loss is a quadratic function of the weights in capital W. This means the loss landscape is perfectly convex. It has a single global minimum, where the loss is exactly zero, and that minimum is reached when capital W is exactly the inverse of capital A. Now, what happens if capital A is singular, meaning it is non-invertible? In this case, capital A collapses some dimensions of your input vectors to zero, which means that information is permanently destroyed. Because of this collapse, you cannot reconstruct the original vectors perfectly, so the loss cannot reach zero. However, there is still a unique minimizer in terms of the minimum possible loss you can achieve. This is solved by the Moore-Penrose pseudo-inverse. The loss landscape remains convex, but instead of a single point where the loss is zero, you have a flat valley of minimum loss. There are infinitely many matrices capital W that can achieve this minimum loss, because any weights acting on the collapsed dimensions do not affect the output. Does that distinction between the invertible and singular loss landscapes make sense?
Yes, that's exactly what I was thinking. Thank you.
You are welcome. It is a beautiful intuition, and it leads directly into your next question about how this applies to large language models. When we have non-square matrices, say an n by m matrix where n and m are not equal, we are either projecting up into a higher dimension or compressing down into a lower dimension. If we compress down, information is mathematically destroyed, just like in a singular matrix. In a transformer, we can think of the hidden states as a continuous vector space where tokens are transformed at each layer. When we use rotary position embeddings or rope, we are applying a rotation matrix to the query and key vectors. Because rotation matrices are orthogonal, they are perfectly non-singular and preserve the lengths and angles of the vectors. This means the spatial relationships are completely recoverable and nothing is destroyed. When you think about tokens as continuous transformations, what specific part of that process feels most confusing or curious to you?
Well, how do I say? So in the coconut paper, they're focused on, how do I say? They allow the model to think to reason in latent space. And they use like the output of the repeated transformations. And well, I'm curious how like potentially like lossly that is, I guess, or lossless it is. Like, is the transformation can can the transformer be undone? It does like is that possible? Does that make sense?
That is an excellent question, and it gets to the heart of what one thinking in latent space means for information flow. A transformer block involves several operations: linear transformations, which are matrix multiplications, and nonlinear activation functions like GILU, as well as the softmax operation in the attention mechanism. While a square, non-singular matrix multiplication is invertible, the nonlinear activation functions in the softmax are inherently non-invertible. They transform the data in a way that cannot be perfectly reversed, meaning some information is lost or irreversibly changed in each step. However, the thinking in latent space approach, as described in the coconut paper, avoids the most significant source of information loss in a typical autoregressive transformer, the discrete token generation step. Normally, after processing, the model applies a linear layer and
Yeah,
softmax to
yeah, yeah,
predict.
yeah. I understand that. Um, so how do I say this? Okay, so what if we didn't do softmax? You know what I mean? Like what if I don't what if we used an invertible transformation inside of the transformer? For our is it are you referring to our activations? Is that what makes it non-invertible?
Yes, the activations like GELU or RealU are a major source of non-invertibility because they squash negative values, destroying that distinction. Softmax inattention also collapses information by normalizing scores.
Oh, but then
If you remove
also all of the numerical precision things that we do breaks invertibility at the same time.
Yes, absolutely. Floating point quantization, like going to FP8 or ternary weights in BitNet, introduces rounding errors that permanently destroy information. If you remove the nonlinear activations in softmax to make the transformer perfectly invertible, you would be left with a sequence of linear matrix
Okay.
multiplications.
I think
Mathematically,
I think I'm recalling what I was interested in is so in a, you know, it's like a bit of a abstract thing, I guess, but if we did if coconut went well enough, let's do an experiment in our minds. If coconut went well enough of reasoning in latent space, then I'm sort of curious about is could you argue that you only need one transformer? Because, I'm curious if so how do I say? A a a matrix and its inverse multiplied together is the identity. It's equivalent, you know? And a single vector can be put inside of a matrix and then its output put back into the same matrix, you know? And I guess in that, what's it called? Those that power operation of a matrix is how we get the eigenvalues, I think. I'm also curious about that. Um, but I'm curious about that, but I'm also curious about is, could you take Coconut so far that you have one transformer and then you just allow a very large number of latent space reasoning tokens before a final, um, you know, regularly transformed token. Do you see where I'm going?
I see exactly where you are going, and it is a profound concept. You are describing a recurrent transformer where a single shared set of weights is applied repeatedly to the latent state, step after step, to let it think before outputting. When you apply the same matrix repeatedly to a vector, you are performing power iteration. Over many steps, the vector will naturally align with the direction of the matrix dominant eigenvector, the one with the largest eigenvalue. If that eigenvalue is greater than 1, the vector explodes. If it is less than 1, it vanishes. To prevent this collapse and allow complex reasoning, a recurrent transformer needs nonlinearities and normalization at each step to keep the vector from just collapsing into a single eigenvector. If you have those, you can indeed use a single transformer block repeatedly. This is very close to models like universal transformers or Albert, which share weights across layers. In Coconut, doing this over many latent steps allows the model to perform deep, sequential computation
Okay.
using the same.
But in that scenario, we lose the linear algebra properties. We lose information. It's no longer a lossless pass.
That is exactly right. It is no longer lossless. But in deep learning, this loss of information is actually a feature, not a bug. If the transformations were perfectly lossless and invertible, the model could only perform linear coordinate changes. It could never compress, abstract, or make decisions. By
Wait a minute.
introducing
Yes, I understand that nonlinearity. I think you may be conflating things. I understand that nonlinearity is what allows for the flexibility, but I would almost say that the loss is something that's accepted, not designed. The design is the nonlinearity for flexibility, but what's it called? And let me go even further. When I'm describing this inverse, I don't strictly mean can it be inverted using linear algebra. If, for example, the sigmoid activation function has a inverse, then I'm curious if the final function that characterizes the transformer is invertible mathematically, not what's it called? Because, for example, when you use ReLU, it's mathematically not invertible. I'm curious if there is a point in which you could design it to be invertible.
Yes, you can absolutely design a mathematically invertible neural network. There is a whole class of architectures called invertible neural networks or normalizing flows designed specifically for this. To make them invertible, they use special coupling layers and invertible activation functions, like leaky rel or ELU, which do not collapse negative values to zero. If you build a transformer this way, you could run it forward to generate a thought, and then run it mathematically backward to reconstruct the exact input state. However, in a standard transformer, the attention mechanism softmax is a major bottleneck for this. Softmax exponentiates and normalizes, which maps infinitely many different input vectors to the exact same output probability
Well,
distribution.
I guess I'm also a little bit curious now as well about if is that loss of information good? I'm not, I'm sort of curious about that. Is, I would almost say in theory that you don't want to lose information. I can appreciate the value of chaos, I guess, of like entropy, but and like, that allowing for new things. But I would almost say like what's it called? Instead of destroying the information, why don't you sort of like focus on different parts of the information? and then you would get the same thing, you know what I mean? You'd be able to do more things without the loss, you know?
That is a very sophisticated perspective. You are describing the difference between destroying information and routing or projecting it. In a high-dimensional space like a model's hidden dimension of 4096, you do not actually have to destroy information to focus on a specific concept. Instead, you can project the data into a subspace where only the relevant features are active while keeping the other information preserved in orthogonal dimensions. This is exactly what the attention mechanism does. It acts as a dynamic projection, focusing on specific features without necessarily erasing the rest of the vector space. If you keep the transformations invertible, you preserve the entire history of the computation. The model can shift its focus back and forth without ever forgetting where it started. Do you think this kind of high-dimensional routing is what allows LLMs to maintain such complex multi-step context?
Well, yeah, so like let me keep going is as far as, maybe you can confirm this for me as well. The inputs stay the same. You still input a just extremely large, sparse tensor when you're doing the next token prediction. Like the size of the inputs are the same, but the contents are different. Where you know you're designing it to output the next token, and you're sort of like masking or whatever if it gave non-zero outputs for future tokens in a way, I guess. That's sort of part of what I assume is that in this like next token prediction is like, if you only have two tokens in your sequence so far, but you can afford 10,000 tokens, is that every other token is zero. And then that gets like multiplied and, you know, nullified by the fact that it's zero.
Actually, in modern transformers, we do not feed in a sparse tensor of 10,000 tokens with zeros for the empty slots. Instead, we only feed in the actual tokens that exist so far. If you have two tokens, the input is a sequence of just two dense vectors. The model processes them, and the causal mask ensures that the first token cannot look at the second token,
Then
but the second token.
how do you handle the dimensions for the actual linear algebra if your sequence length is no longer appropriate? Is it like adaptive attention? Like you change the scale at which you do the operation, and you just like, I guess, you append the matrices that you perform the operations on as the sequence grows.
Yes, that is exactly how it works. The weight matrices of the linear layers, like the projection matrices for queries, keys, and values, are fixed in size. They only care about the hidden dimension, which never changes. When the sequence grows, we just stack the new token vectors along the sequence dimension. The attention operation is what scales dynamically. We compute the dot products between all queries and keys, which creates an attention matrix of size sequence length by sequence length. As the sequence grows, this attention matrix simply expands, and we apply the causal mask to the new size. So the linear algebra operations naturally scale by appending rows and columns to the activation tensors, while the model's weights remain completely static.
I see. Oh, wow, because the attention matrix. I see. Because the attention matrix, it can be as big as it wants to be, but you never, what's it called? Yeah, I guess everything will be okay. It's like as sequence length changes, it's just all adaptive, I guess. Okay, wow. But hmm, isn't that strange though? So, like, what's it called? So, for example, you have the final model, but you have some early tokens. What happens? You know what I mean? It's like you have a once the model's been trained to be able to use a large amount of context, then what? You like what's it called? Do you only use particular indices, or is the scores matrix never, how do I say? The scores matrix is never, it's never saved. It's something that's computed and then tossed. And so that's why it's completely fine for it to be dynamic. But the queries and keys are for each token, but they're only for the tokens that are in context. And that's why you sort of have the cache.
You have nailed it perfectly. The attention scores matrix is computed on the fly and then immediately discarded after we use it to weight the values. It is never saved as a model weight. And your intuition about the cache is exactly right. This is the KV cache. Because the weights are static, the query, key, and value vectors for the past tokens never change. So instead of recomputing them at every single step, we save the keys and values in a cache and just append the new token's key and value to it. This is why the sequence length can grow dynamically
But that's
without a
also, that's very interesting. That's, you know, that sort of construction is also very not native to linear algebra, if that makes sense. You know what I mean? Where we're sort of like appending things? Or is it going to be completely fine because the dimensions that carry about each other, like the particular sequences, take, you know what I mean? Is like, how do I say, the 10,000th token almost has its, stays in its own dimension space in a way, even though it can pay attention to the other ones. The operations are done for the 10,000th token, whatever value is in that index. So, and like many different tokens will end up in that index, so it all sort of like blends together. I don't know.
You are touching on a really deep point about how transformers represent sequence position. In pure linear algebra, a matrix multiplication does not care about the order of the rows. If you shuffle the tokens, the linear layers will output the exact same vectors, just shuffled. This is why we say transformers are permutation invariant by default. To fix this and make it native to the linear algebra, we have to inject position information. This is where rope or rotary position embeddings comes in. By rotating the query and key vectors based on their index in the sequence, we encode the position directly into the angles between the vectors. So, even though we are just appending tokens to a list, the linear algebra knows exactly where each token is because of those rotations.
Okay,
The
I think that's all for today. Um, I think I think mostly what I was curious about is the recursive transformer, and that's something that's interesting to me. I'll keep that in mind. Please write a note for me to come back to the idea of the recursive transformer and what we were talking about today about how it's adaptive and whatnot. Um, I have a few open questions on that that I'd like to circle back to.
I have saved that note for you so we can easily circle back to the recursive transformer, power iteration, and how the dynamic sequence length fits into it. It was a fantastic discussion. Let me know whenever you are ready to dive back in.
Um, I'm feeling very lukewarm about today. I think tonight's gonna be rough for me. I'm gonna post this. Um, we didn't really do anything today. Hopefully the coconut run finishes soon. Um, hopefully we can do some cooler linear algebra something. Ah man, I don't know. I'm done for today. It's 10. This video's long as well. Ah man. There's something going on. It is curious. We wanted to start with the convex and singular, so that's nice. Even though I don't know the definition of a singular matrix. Um, I get flamed in class for that. Yeah. Just because I'm curious on the, I don't know, like there's like parts of like the nature of the architecture where I'm trying to think about things in like information and like interactions of information and what's preserved and what's lost and that kind of stuff. Um, it doesn't seem very math native, feel like it kind of does, because if it's like off of index and like the way the operations, even if it expands, they never interacted with each other to begin with, you know? So appending doesn't change things. But I don't know, when you think about things like the causal mask, that's like a decision, you know? That's not like a, that is not the brutal lesson, you know? That is not just more data. That is absolutely architecture. Um, so I think, yeah, I think that's part of why I'm very interested in designing designing my own architecture. That would be really cool. um, yeah, I'm gonna call it. Today's rough. Unfortunate. You can't win them all. Um, ooh, does that mean I have to come back harder tomorrow? I think it does. Very interesting. Very intense. So tomorrow I'll come back harder. Oh my goodness, do I need a thumbnail? Wait, this is perfect. I see. I like that that's organic. Um, let's see. Oh wait, I'll take it after. Okay. So you'll have a thumbnail. I'll hold it up. Um, I might LARP that this, I might LARP the title and like pretend that I had a good time. I don't know. I think my description will just be gonna come back stronger tomorrow. Um, but that's all. Have a good one. Hopefully, hopefully we're more locked in soon. Um, I think when I'm on the train, I'm starving, dude. I think when we're on the train, I'm going to think about how I can take care of alt chat and how I can like do the videos better. I'm not sure tomorrow will be locked in because vault chat won't be fixed by tomorrow, and there's just a few things. But yeah, okay.